Good evening, everybody. Welcome. I'm very glad you're all here and you could resist the nice warm weather to hear a lecture about nuclear fusion. It's a co-production of Studium Generale and Arago, the Physics Study Association. Topic is fusion energy. As you all know, it's the engine of the stars and maybe the energy of the future. That's one of the questions we pose to our speaker this evening. There are, however, a lot of challenges to overcome. Imagine you got a plasma of about 150 million degrees and you have to contain it somewhere in a machine reactor, which is not allowed to touch the reactor itself. That's a very complicated problem. At the same time, you must also distract energy from it to heat up water or so to produce electricity. That's also pretty complicated. So we have a lot of fascinating physics, but also engineering this evening. It will be a combination of both. I'm very happy that Professor Marco de Baar came all the way from Eindhoven to Enschede. He is leader of the nuclear fusion program at DIFER, and DIFER means the Dutch Institute for Fundamental Energy Research, and he's also a full professor in mechanical engineering at the Technical University of Eindhoven. So, Marco is one of the fusion experts in the Netherlands. Marco, the floor is yours. I'm very curious what you are going to tell us about nuclear. First test your.
Well, it's really a pleasure to be here. The reception that I received from Peter was also immaculate, I would say. Lovely asparagus. I was told it was local produce, so very good. In today's presentation, I would like to discuss some of the more technical aspects of fusion. As Peter already said, I'm a professor in the mechanical engineering department where we work on dedicated controllers for tokamak plasmas. I will try to introduce to you why we need to build those controllers, and I will try to elaborate how we come to these controllers. Of course, this could be completely irrelevant to you. I mean, I had to pick a topic and I thought this could be nice. If you want to know anything else, feel free to ask at any time. And I will try to deliver. I'm not guaranteeing that I will deliver, but I will try to give the information that you want to have. Yeah? Also, if there's something unclear, at any time, ask questions. I would like to have questions throughout the meeting. Better to explain them now rather than to wait and then things get a bit unclear. So let's start with a picture. This here is the ITER construction site of 2 months ago. ITER is the nuclear fusion reactor that we are building as a world community, as a global community in the south of France. So ITER is being built by Europe, Russia, the United States, Japan, China, and there are also other partners who would like to join in, such as Kazakhstan, Iran, Brazil. So there's a lot of international attention, a lot of flow of capital, but also flow of talent towards ITER. And you see here the scale of what we're trying to establish. I will discuss in some detail what we're trying to achieve in this area here. This is where we're going to construct the tokamak reactor, especially what we're going to do with the plasma inside that reactor. But I think it's already interesting to see the scale of the program that we're dealing with. This here is a cartoon showing the front side of the part that you see over here. So on top of this bioshield where the tokamak is going to be, a second very big hole is going to be constructed, which will give space to all sorts of services, heating systems, power supplies, cryogenics, diagnostics. Yes, please.
What's the budget?
20 billion.
Euro.
Yeah. We are not too bothered about 10% at this point. So the way it was set up, when the ITER contracts were signed, at that point, people made calculations what the value of the different components would be. And they were then allocated to different partners. And then from that point on, we were discussing ITER credits. So if the dollar or the euro jumps up and down, it doesn't matter because that thing is worth so many ITER credits. So it's a bit difficult to give an exact estimate, but 20 billion is a fair estimate. So what are we going to achieve in ITER? What you see here is the reaction between two hydrogen isotopes, deuterium, 1 proton, 1 neutron, and tritium, 1 proton and 2 neutrons. If we bring them close together, and we have to overcome the Coulomb repulsion, of course, but if we bring them close enough together, we get a fusion reaction where we produce helium, a neutron, and a lot of energy that is in the thermal velocities, in the velocities of the helium and the neutron. The helium will stay in the plasma. It should collide with the ambient plasma and transfer its energy, leading to heating of the plasma. The neutron should impinge on a so-called blanket and have a reaction with lithium, producing helium, a bit of energy, and tritium. And of course, the idea is that in the end, the tritium will be fed back into the reactor. In fact, this neutron into the blanket producing tritium is one of the Achilles tendons of fusion. So there are many Achilles tendons, many things that could really go wrong. This is one of them. I will not discuss it today, but it's a really big technological challenge. Anyway, I mumbled something about the right conditions. So what are those conditions? First and foremost, we want to have a high temperature of our fuel. 150 million, 200 million degrees Kelvin. Now you think that that's hot, but let me reassure you, that's not the problem of fusion. When I was working at JET, I could produce discharges with a core temperature of 400 million degrees already in JET. So that is not the problem of fusion. It becomes complicated if you also want to have the right density. And the right density is, in this case, in the order of 10 to the 20th particles per cubic meter. And finally, we want to be efficient. What does it mean? If I store a certain amount of energy in my fuel, I need a certain amount of power to maintain that. And the ratio between the stored energy in my fuel and the power that I need to couple into my plasma in order to maintain that is a time scale. And the time scale that we need to achieve for ITER is 4 seconds. So we need to satisfy these criteria simultaneously. Yeah, come on.
The density is low or high?
Well, in terms of particles per cubic meter, it is very low. But for fusion plasmas, this temperature at that density is very high. Yeah. The triple product of these 3 parameters, of the temperature, the density, and the energy confinement time, is in fact the fusion figure of merit. So let's have a look at how the fusion figure of merit has been developing. So what you see here on the vertical axis is the triple product, this fusion figure of merit, as a function of the central ion temperature. And what you see here are regions where we compare the amount of energy that we couple into the plasma with the amount of energy that comes out of the plasma. So this here is what we call the capital Q. Oh, sorry. Ik heb de dikke vingers. The capital Q bound of 10%. So here we're pumping 10 times as much energy into the plasma as that we get back in fusion reactions. Here we are breaking even. We get the same amount of fusion power as that we couple into the plasma, and this is where ITER is going to operate, and here we will get 10 times as much power from the plasma as we couple into the plasma. Now, if you look at these discharges, you see what I just told you. It's not so difficult to produce very hot discharges, but they are at too low density. In order to get them into the right bound of capital Q, we must make them a bit cooler at the same density. So in fact, we're producing too hot plasmas in present devices. But what you see here, at least, is a significant, I would say a dramatic improvement of the performance of fusion plasmas. Of course, this has to do with the machine size. You will not be surprised that these are early, rather small experiments, and that these are present-day, rather big experiments. But it also has to do with continuous improvement of the discharge. And that is, in fact, what we're going to discuss today. What do we do? How can we improve discharges that we can operate at various, let's say, high values of N to T? Now, yeah?
When you talk about the amount of energy that goes into the reactor and how much you get out of it, are you talking about the theoretical amount of energy that you get out of it or the actual amount?
Well, both. Let me go back. Here, where's my, yeah, here, there are a number of jet discharges that were really done at 50-50 deuterium-tritium. And we really could measure the fusion power and compare that with the heating power that we coupled into the plasma. So that was measured. Here we have a JT60 upgrade discharge, which was done in pure deuterium, but we had to model what the DT fusion rate would have been. So it's a bit of both. Here you have the real thing, here you have modeled stuff. TFTR was doing deuterium-tritium. D3 is a modeled, and so on. So it's a bit of both. Yeah? So let's first explain what magnetic confinement is. So didactics, I have to admit, is a bit of lying. And here I'm going to lie a bit, because this is not how we do it, but it explains what we want to achieve. So here you see a tube where I have some ionized particles. The red big chunks are the ions, and the yellow small ones are the electrons. I achieve that, according to this picture, by microwave heating. This is not how we do it, but okay. Anyway, the problem is, in this particular case, my particles are free to move, and they can impinge on the wall at any time, and as a consequence, I have very significant loss processes. So the power that they couple in will not yield a very big stored energy. So I need a trick, or as Tom Post would say, we need a list. And the list is the magnetic field. What we're going to do with the magnetic field is charged particles in the magnetic field start to gyrate, and they're confined to the magnetic field within their Larmor radius. Of course, the particles are free to move along the magnetic field, so they are, in the end, producing end losses. And we need to figure out how to deal with those end losses. The way that is done in all those machines that you saw on the higher end of the graph is by producing a toroidal device, and the toroidal device will deal with the end losses. Now, this seems like a very good trick, but in fact, we have now a different problem, and we're going to deal with that problem now. The problem is that if you have a curved magnetic field and you have gyrating particles, that a drift starts to emerge. Particles start to, I'm not sure if I have a slide. Let me see, no, I don't have a slide. So what happens is that my gyrating particle will get a slightly different radius on the high field side, and then a slightly lower radius of curvature on the lower magnetic field side. And as a consequence, it starts to drift upward. And that means that after a while, my particles are pumped upwards instead of flowing freely in toroidal direction. So what we need to do is we need to drive those particles that are flowing upward down, and the particles that were flowing downward, we need to drive up. And we do that by introducing a second component to the magnetic field. So here you already see the tokamak concept. These big blue coils are producing a magnetic field in toroidal direction, in the main direction. So this is the toroidal field that we set up by those blue coils. Then we have the green coils, and those green coils are the primary of a transformer. So we ramp the current in those transformers, and as a consequence, we get an electrical field in the fuel. And the electrical field starts to drive a current, also in this direction. Right? So the plasma, the fuel, is the second coil of a transformer. And that then gives me a second component of the magnetic field. It's a poloidal component of the magnetic field. And the consequence is that my magnetic field is now doing a helical trajectory. And that means that particles that want to drift upwards are pushed downward by the magnetic field. And particles that want to drift downward are pushed up by the magnetic field. And as a consequence, this poloidal component of the magnetic field is mixing against these drifts. So the current in the tokamak is an essential ingredient. Now finally, when you have a ring of current, it wants to expand, right? So we need to push it back. And in order to push it back, we have additional coils, indicated here in gray, for example, that are used to position the plasma in radial direction, so keeping the ring in its place, in vertical direction, but also to shape the plasma and to deal with this task that Peter explained, the exhaust of heat and particles. This is a set of coils not indicated here, but typically would give a very high-order structure of the magnetic field in the diverter. And that is effectively your concept of a tokamak. Now, what do we get when we have these weird magnetic fields? Here you see a set of surfaces, and those surfaces have magnetic fields that are twisted, as I indicated. Why do I plot different surfaces? Well, what we're now doing, what we're setting up here, is a system that is confining the hot plasma using the Lorentz force. So I have grad P equals J cross B. If I take the dot product with B of that equation, by definition, that is 0. So I have surfaces of constant pressure in which my magnetic field lines are embedded. And this is a very important concept. It brings the transport, which was, let's say, a few slides ago, here, was a 3D problem, changes that into a 1D problem. I have a surface of constant pressure. Due to these field lines and the very fast transport along the field lines, also my temperature is equilibrated very quickly over the surface, so it's also constant temperature. And effectively, my transport properties are 1D, my transport equations are now 1D equations as a function of those surfaces. And that's a very, very important concept. Now, what you need to know is that we can solve the equations of those surfaces, but it's a very cumbersome, nonlinear differential equation, and it's definitely something we cannot do in real time. We can estimate in real time, but we cannot solve it in real time. Now, let's take a step back. Let's follow a magnetic field line. I'm going to make a Poincaré plot. Let's follow a magnetic field line, which is, where's my pointer? Which is on this surface. And this surface has a symmetry which is very close to, let's say, 3. So here's my magnetic field line starting, piercing in the screen. We follow the field line in toroidal direction, and now we pierce here. We do it again, and now we pierce here. And then we end up there, and then we end up there, and so on. What I can show is that if I have a little box of size epsilon, my field line will penetrate my box. And then you say, oh, you must take a smaller box, fine. Then we have to wait a bit longer. But I can show you that my field line will penetrate that box. So in other words, my surface is built up by one field line. Now, very close to that, I do the same thing. I start here, I go there, and I have to be precise, I end up there again. Here, there is a resonance. Effectively, one field line is setting up a finite length, and my surface is built up by a number of magnetic fields. Now, the response of these surfaces to perturbations is very different. In the first case, if I, let's say, would have a handful of particles which I would throw on that surface, it would be spread out equally over the surface simply by following the field lines along the surface. In the second case, if I have a small perturbation, it stays on my field line. And the effect of my perturbation becomes rather big. Now this is the last, keep this in mind. We'll come back to that in a minute, because it's going to bring a significant problem around. Now this is a plot of ITER. You will recognize a number of the components that I just mentioned to you. Again, so you here see the primary of the transformer. You see the big coils that are used to set up the toroidal field. You see in pink here humongous coils that are set up to produce the poloidal field. Just for the scale, and also to tell you how problematic fusion is, one toroidal field coil is a superconducting structure that weighs more than an Airbus 380. And we have 20 of them. And then these pink coils are even bigger and also superconducting. I think it's nice to mention that those superconducting coils were in a very poor shape and that Twente has saved them. So you can be very proud of that. Okay. Now let me give you, are there students here? Yeah? Yeah? Okay, just, I'm going to do, didactically this is shit what I'm going to do, but just that you know what we're doing. So if you want to consider a project with us, you can always call me and we can set up something. So one of the big problems in fusion is that if we produce fusion power here and the alpha heating is heating the plasma, in the end, the heat of the alpha particles will be deposited in a very small region, which we call the diverter, and you have really incinerating conditions there. We have in our institute a linear device which produces exactly the conditions that we have in front of the diverter target. So the same power density, the same temperature, the same density of particles, and also dynamic fluxes that can be up to 1 gigawatt per second can be reproduced here. And this is also a superconducting coil. This was also a big problem, and this was also saved by people from the Twente team, so we're very grateful for that. So if you're interested, for example, in material science and the effect that plasma has on materials, this could be an interesting part. We also are very keen on building state-of-the-art instruments, and these instruments are being used for physics studies, but also as sensors in real-time control loops. And this is something that I will be dwelling on for the coming 40 minutes. And finally, we are very keen on tractable and accurate models for plasma scenario prediction, optimization, and control. So the key thing here, and this is what I'm going to elaborate on, the key thing here is that when physicists make models, they do that to understand the physics better and better. When engineers make models, they do that to optimize the system. And what we're really trying to do in our workplace is bridge those physics models with engineering models to get, in the end, better performance. And that is what we're going to discuss in the second part of the presentation. So, time for a problem. Let's have a problem. So we said we need high values of N to T, right? So let's first consider what happens when we go to high NT? What happens when we go to high pressure? We'll deal with TOR later. Now here you see a typical result. This is a jet discharge, where we have a heating system, which is called the neutral beam injector, and we inject a few megawatts, more megawatts, 10 megawatts, 12 megawatts, and so on. What you see here in this top graph is the stored energy in the plasma. And you see that as soon as I crank up the power, the stored energy keeps increasing. Until, at some weird moment in my discharge, although the injected power keeps increasing, the stored energy crashes down. What's happening there? Well, there is a clue. I can use magnetic pickup coils. We have zillions of magnetic pickup coils all over the machine. And I can connect these magnetic pickup coils in order to be very sensitive to certain structures that are associated with the magnetic resonances that I discussed a few slides before. So for example, the black trace is associated with magnetic resonances that are associated with the so-called 1/1. Whereas the red trace is associated with the magnetic resonance that is associated with the magnetic resonance that is a 3/2 structure. Means that I go round 3 times in toroidal direction in order to do 2 poloidal orbits. Now what you see is that when my power is being cranked up and my stored energy goes up, initially I get a bursty instability with this 1/1 structure. We know this instability very well, it's called the sawtooth, but that is not what is giving us problems. However, at some point, the saw teeth are getting so big that they are effectively a gong. When you hit on the gong, you produce all sorts of higher order resonances. And when I produce a higher order resonance, suddenly I can produce a second structure, this 3/2 structure, and that is breaking down my confinement. Here you see a cartoon of what we are dealing with. So here again you have this a cross-section of my fuel. And when we have this instability, what you see is that we get effectively a higher order magnetic topology, where we have an extra magnetic axis. Initially we had one magnetic axis here, now we have a second one in the so-called magnetic island. Now we understand this island rather well. What we know is that in the so-called X points, here, we have a surplus of current. Not a lot, but we have a surplus of current. Whereas in the so-called O points, where this magnetic axis is forming, we have a deficiency of current, right? And what we're going to do is we're going to build a control system that will find the O point and drive current in the O point in real time. That's what the first task that we're going to do. So, what do we need? A sensor, actuator, and a model. Sensor. So first, the principle is the electron cyclotron resonance. I was very keen to tell you that charged particles gyrate around a magnetic field. When they do that, they send out a bit of electrocyclotron power with either this frequency or an integer multiple of that frequency. Also, they're absorbing this sort of frequency ranges. So the first thing that we're going to do is build a radiometer, a sensor that is measuring the EC emission. So here you see a cartoon of my plasma column. This here is the magnetic field falling off from the center of the tokamak to the edge of the tokamak. I know that if I fill my radiometer horn, I have, in the right conditions, a linear relationship between the EC power that I measure and the local temperature. And what I now do is I build a radiometer that looks in little bands, let's say bands of 3 gigahertz, and I measure the ECE power, and using the magnetic field, I have a local and time-resolved measurement of the temperature. Now I need an actuator. The resonance condition for EC power that I inject into the plasma is given here. So you have a relativistic correction for the absorption. Here you have the order, so we can do it 1, 2, or third harmonic. And very important, you have this vector which is associated with the angle of injection. Let's go back to this slide. Here you have the parallel velocity. And what you see is that I can choose a condition where specific parallel velocities are resonant. Now this is the trick. This is my velocity space distribution. I have particles in vertical velocity direction. I have particles in parallel velocity direction. Using this criterion, I can select a chunk of particles with a specific parallel velocity, and I can pump in microwaves that are associated with the gyro motion. And by doing that, I pump them in the perpendicular direction. And the trick is that if you do that, if you make particles faster in the plasma, they become less and less resistive. So this is a trick to create a population of particles that has a very specific parallel velocity and is not feeling resistivity. I'm starting to drive current here. Now the system that I use for that is a gyrotron, and I will, the only thing that you must know is that if I use my gyrotron, I can deposit a megawatt of power in a sugar cube, and I can slightly tune the launcher to get exactly the right current. Now I need a model to understand where I'm going to drive my current. Now here you see the temperature in a so-called Textor discharge. Textor was a discharge, was a tokamak in Jülich in Germany. It doesn't exist anymore. We did a lot of experiments there. And here you see the distribution of the temperature from the center to the edge of the plasma in case there is no magnetic perturbation. If we have a magnetic perturbation, it really matters if you observe the temperature through the O point. In that case, you get this flat part, or if I look through the X point, because then I will observe a gradient. Of course, my plasma is spinning, and as a consequence, what I observe is a pivoting motion of my temperatures. Here you see in a Textor discharge, measured with the radiometer that we've built for this purpose, the development of a magnetic island. We blow it up here, and you see indeed that we have a number of channels that are oscillating. Oops. Oscillating. Here we have channels that are oscillating with the same frequency, but in fact they have this 180 degrees phase jump, and here we have something that is hardly oscillating. That is what you're seeing here, right? Channels oscillating with the same frequency as here, but in counter phase, and one that is hardly oscillating. This here is the signature of where my mode rotational surface is. And now we're going to do the trick. We're going to build an instrument in which we combine a megawatt of heating and current drive power with a radiometer branch that's going to measure with a nanowatt or 100 picowatt. Here you see how we've done it in Textor. We have a system where we use 2 dielectric plates. Every plate gives 25 dB with a high quality, and then the power is so low that you can use a notch filter. So the way it works is my heating system is transmitting through the first dielectric plate. In this direction, the dielectric plate is transparent. We find, via this system of mirrors, the plasma. The plasma is emitting, it goes back, and is being put in the radiometer. Now the only thing that we need to do once we've set this up is we need to use a signal to steer this mirror such that we get the phase jump at 140 gigahertz, which is the gyrotron frequency. Irrespective of the equilibrium, which we don't know, irrespective of the wave propagation, which we don't know, irrespective of the calibration of the steerable mirror or errors that we have produced in the optical line, we will be on target. So we are extremely robust. Does it work? Here you see a nice experiment, again in Textor. Textor had a unique feature. They could use a dedicated coil to produce tearing modes, to produce these modes that are unwanted. And then we can experiment with them. So here they ramp up the current in that coil, and at some point you see, boom, here's the mode. Here you see in this box at what location in frequency space we observe the mode, where we see the phase jump. Now, as soon as we have the mode, we see that we find the mode at, in this case, the channel of 143 gigahertz. At 2 seconds, indicated by the dashed line, first we allow the controller to move the mirror. Fine. Mirror is moved, we are on target. Now we have our electrocycling heating beam on the right location. Then, here we switch on in red, we switch on that power. We deliberately choose only 200 kilowatt. If we would have used more, we would have killed the mode directly, but we want to do some experimentation. And now we're going to do a trick. We're going to ramp the toroidal magnetic field. Now you know that if we change the toroidal magnetic field, we change the magnetic resonances in the plasma, we change the electrocycling emission, and we are effectively moving the location of our channels around, and we are changing the electrocycling deposition. Never mind, the controller is simply trying to keep this system on target, and that means that we need to move the mirror in order to compensate for that position. So this is a very simple solution of a tearing mode suppression system. Now we need to get the island heated in the O point and not in the X point. In Textor we could do it very simply with a phase lock loop. Here you see two realizations of that. These are experiments where we really spot on hit the island in the O point and not in the X point. There are, unfortunately, tokamaks that have a way larger bandwidth. In Textor we were limited up to 5 kilohertz. There are tokamaks that have mode rotations up to 20 kilohertz. And there was one tokamak that asked us to build a system to do this with a bandwidth from 5 hertz all the way up to 20 kilohertz. And then this phase lock loop doesn't work. So now this model-based control aspect starts to come in. So far I've discussed actuators and sensors, and I've discussed one static model, but now we have to go one step further. This is an evolution of system and control theory since, let's say, the 1960s. Classical control engineering was set up, typical PID type of controllers for single input, single output systems. Between the 60s and the 80s, the state space formalism was developed, and I will discuss that in a minute. And that allowed first and foremost, to look at larger scale systems, to look at multi-input, multi-output systems, and to apply Kalman observation. And in fact, that's what we're going to do now. We're going to build a Kalman observer. Then, in the 80s and 90s, we did robust control and system identification. We have applied this a lot, but I will not show that today. And then, finally, in the 90s and 2000s, model predictive control was set up. And I will show you an example of model predictive control in a minute. So, what is the state space formalism? This is a process where I have an input and I have an output. The output can be measured. And the key aspect is that if I have an output, it doesn't tell me about the system dynamics. If I want to control properly, I need to understand the system dynamics. We're now going to introduce a concept which is called the state. And the state contains the full dynamics of the system if I don't perturb it. Right? If I know the state, and I have a proper model, which I for now assume that we do, then I can simply calculate the evolution of my system. Now, in general, you can write differential equations of this type. You can extend them, but what you see here is that the variation of the state, so this is where the dynamics kicks in, is a function of the input and the state itself. And this function can be a highly nonlinear thing. The measurement is another function of the input and the state. Typically, we ignore the input because it becomes non-causal. But for general purposes, I included the input here. Now you can linearize this, and then you get a very interesting set of equations. These are the state space equations. My variation of x is a matrix A times my state, plus a so-called actuator matrix times my inputs, and my measurement is another matrix, C, times my state. So my measurement is a projection of my state. And now the question is, can I infer from my measurements what the state is? And this is what Kalman came up with. This is really, I think this is real true genius. What Kalman said is we have the real system, the plant, and we have a model of the plant. We apply the same inputs, which are varying, which are time dynamic, which are time dependent, and I produce a measured output and a modeled output. I can compare these two, and I get a small difference, which I then can feed back in so-called Kalman state update. And what happens if you apply this? After a while, your state converges, and you get that your modeled output equals your measured output. You can set it up such that your model incorporates noise. So in fact, you get an output here, which is noiseless, plus a noise term, and so on. So this is really very neat. You can do this for various diagnostics, various sensors at the same time. So you can merge sensoric information. And the beauty is, you can do this in real time. Here, just to give you a flavor, we apply the Kalman filter to the problem of the rotating modes. How can we infer the frequency and the phase of those rotating modes in various conditions? What you see here is a typical spectrogram of a rotating mode in the Swiss tokamak TCV. So what you see is, of course, we have the ground frequency, we have higher harmonics, we have a noisy background, and we want to extract in real time the information. Now we set up a Kalman filter, and you see here how the Kalman filter managed to find the right frequency and phase in spite of the noise in the signal. Once we had this Kalman filter, we could test how this filter was working on non-ideal data. For example, in Textor, we had data where we had to use a sample and hold bank in order to deal with spikes, and you get these very weird plateaus on the sinusoids. Kalman filter simply deals with that. Here you have what happens when a mode becomes big and it starts to interact with the metallic wall of your tokamak. What you get then is that it starts to decelerate and then unlocks and starts to accelerate again, and then one period later it locks again, decelerates and accelerates again. So you get these very weird oscillations. And the Kalman filter still managed to find those waveforms and also managed to find the frequency variations that were associated with the locking and decelerating and unlocking and accelerating again. So this is a really neat way of doing it, and again, this works in real time. Okay, so how does this relate to ITER? Here you see the systems that are being built in ITER to deal with MHD modes. And you see that it becomes a bit of a beast now. This thing is 5.5 meters long. The cross-section here is a square meter. The thing weighs 25 tons, has 2 rows of 4 waveguides. Each waveguide carries 1 megawatt. And in the end, the power is deposited in the plasma via these 2 movable mirrors that can deposit the power at various locations in the plasma. In total, 4 of those systems exist in ITER, and we have 20, 30 megawatts at our disposal to do MHD control. Can we do more? Yes, we can. So now we're going to ask ourselves, what is the story of tau? We needed to operate at high n-tau-T. We've just managed to effectively eradicate the limits in the pressure, so we can work at high pressures. Now we need to crank up the tau. Now, this is an old cartoon. Initially, tokamaks were only relying on the ohmic power to crank up the stored energy. And the behavior was extremely favorable. In fact, the total heating power had a linear dependency on the stored energy. This was extremely positive. Then we started to add so-called additional heating systems. Neutral beam, I was already mentioned, electrocycling heating. There are more. And this is a problem. So here you see that as soon as we start to go over the ohmic power using additional heating, the stored energy increases way less efficiently than we were hoping for. Of course, if you look at the temperature profiles, the temperature distributions, initially we had some sort of bell-shaped temperature distribution, and with more power, yeah, it goes up. But it's the tau that is really not going up. Fine. Then, a very famous, I think this is the highest cited paper in our field. In the south of Germany, this remarkable observation was done. When they cranked up the additional heating power a bit further, and they had a magnetic configuration using a so-called X point, suddenly a very narrow structure emerged in the edge of the fuel, which lifts the complete temperature distribution. So the gradients in the blue profile and the green profile are virtually the same. The only difference in gradients are induced at the edge, and in fact the stored energy is increased over the whole profile with the so-called pedestal. So why do you see this gradient only in the plasma edge? Very interesting question. This is a true phase transition or bifurcation, very interesting physics, and I will give you a flavor of the physics mechanisms that are underlying this.
Could you do it in 5 minutes?
5 minutes?
Yeah, is that possible?
Yeah, sure.
Yeah.
And was it so long already?
Well,
Okay, okay. Then I have to move on. Then I'll skip this one. The physics that is underlying this is the following. In the plasma, when we start to use additional heating, structures emerge. These are fluctuations in the density and the electrostatic field, and they drive transport. And these are coherent structures. Now, a key task when you want to improve the confinement is that you have to decorrelate these structures. And that's exactly what happened in this particular case here. The structures here were completely decorrelated, and the turbulent transport that was set up by these vortices was eradicated. Now, you have to, I will not prove that, I will just tell you, there are two ways of driving down the turbulent transport. One is momentum input, and the other one is dealing with the current distribution. Momentum input in ITER is very difficult, whereas the current distribution is likely to be controllable. Now, the current distribution has a number of terms. The current that we drive via the ohmic circuits, the current that we drive using our neutral beam injection system, the current that we drive using our electrocyclone system, and the current that we drive via the bootstrap current, which is effectively you drive current when you have a pressure gradient. And that means that you have now a system that is set up by a set of co-evolving nonlinear partial differential equations, because the temperature, the pressure, and the J profile are coupled, nonlinearly coupled. And now we need to set up a controller to deal with that. And we fall back on the same concepts. So this here, effectively, is a Kalman filter. Now we have a Kalman filter that has the physics of the transport equations. We have, again, actuator comments that go to the real system, the tokamak, and to my model. I have a number of diagnostics, and I can compare my diagnostic signals with my physics output. And once I do that and I've converged, I have knowledge of the complete dynamics of the transport equations. And now I can start to control the transport in my plasma. I write here advanced control. I will give you an example. I will skip this. The advanced controller that we use is a so-called model predictive controller. Once we have the nonlinear equations and the nonlinear state, we can exploit the fact that in the tokamak we work along trajectories. We know in advance where we want to go with the system. And we can linearize those nonlinear equations around that trajectory. Then we get a set of linear equations that we can use to predict. These equations can be evolved numerically faster than the tokamak. So here is the way it works. I have a present state. This is my reference, the blue one. And I'm here, and my model predictive controller can now anticipate the best way of approaching my reference trajectory. This is very important, this predictive aspect, because now suddenly I can avoid constraints in my actuator park. I can simply use the power that I have available for a controller task, and I can avoid limits in the plasma operations, such as MHD modes. Now here you see an example of such a controller that we applied in the Swiss tokamak TCV. What you must know here is that we simultaneously controlled the distribution of the current and the total stored energy in the plasma. And we could do that with great precision in the current and with great precision in the beta as soon as we allow the controller to work. And here you see the name of the game. I'm going to be, I think this is the last slide. Here you see the name of the game, because what we now have set up is a controller that is not really glued to a specific operating point. We have the model equations, and we are in a position that we can work over the whole nonlinear variation of the system. So what we have here is effectively a current density profile controller. We call that Q, forget about it, it's the current density. At some point, we allow a magnetic mode to evolve. Now, this is very important because up to now I was using 4 of those big systems to control the current density distribution. And at this point, when the mode emerges, I need to allocate one source to the NTM problem, and I need to control the current density profile using 3 sources. So my whole controller problem definition changes. Nevertheless, the system manages to deal with that, and then we have another island emerging a bit later under slightly different conditions, and again the controller manages to do that. So I will, I will forget about it. This is 5 minutes, right? So let me come to conclusion. I apologize for being a bit late. Tokamaks feature various challenges, especially from a control perspective. We are dealing with distributed systems, so systems that are described by PDEs. We have plant limits because we have limited power. We have limited sensor access, and we have actuator constraints and actuator sharing problems. The point I want to drive home to you is that modern model-based control technology allows us to deal with some of these issues. The starting point is always the formulation of a dynamic input-output model, and then once we have that model, we can synthesize controllers, do state observation, test controllers in numerical environment before we put them on the machine, and finally, we can do predictive control. Thank you very much.
Thank you, Marco. Sorry for speeding you up a little bit, but we have
okay.
time for questions.
No,
it was very interesting. When I came into this lecture room, for me, a plasma was just a hot blob, some kind of hot thing, but you explained there are a lot of structures inside it, and it's very difficult to control it, but it can be, that's very one of your slides, there was all the patterns inside the plasma, which can be very precisely controlled. But one question to start with. How does it work? You have the plasma, and then suddenly you've got fusion inside the plasma. You've got a lot of heat.
Yeah.
How does it work? Is it some kind of explosion inside the plasma, or does it go gradually? How do you control that fusion process? Because it generates a lot of energy.
Well, this is already, first and foremost, no explosions.
Mm-hmm.
It goes gradually, because you produce fusion, and then your fused products, your fusion products, need to collide with the ambient plasma, but that goes with the collision timescale, and the collision timescales of those alphas are very, very long.
Mm-hmm, mm-hmm.
And then, on the longer timescales of collision, you start to heat up your plasma, and you start to go to a regime where you have more and more fusion power.
Mm-hmm.
And this is the moment when you start to ramp down the power of your additional heating systems.
Mm-hmm. Okay.
So the more fusion power, the less input power, and finally you see that you cross each other, and you start to produce more and more, and couple less and less.
Yeah.
That's the idea.
Okay. That's clear to me. If there are any questions, please raise your hand. Yeah, go ahead. It has been a Manjana machine.
No, this is a very good question. So first and foremost, ITER is an experiment. And what are we going to experiment? We're going to experiment exactly how this self-heating process works. I mentioned that we have turbulent modes, and these turbulent modes are driven by gradients in population. What we're now going to do in ITER is we're going to add another population, the alpha particles. And those alpha particles can also drive MHD modes. And now one of the questions is, how do these MHD modes lead to losses and non-ideal behavior? We're convinced, based on modeling, that those losses will be less than 7%, and those losses are taken into account in the predictions, but experimentally we need to show that. So I'm quite sure that we will produce the fusion power. The question is, can we then control the discharge and keep the fusion power at the right level during, let's say, half an hour? And very important, in a real reactor it's also a sensor problem, because it's very difficult to get the sensors in. And also there I want to push this model-based observation technology.
Mm. And Marco, when do you expect ITER will produce more energy than it costs? What?
The first plasma is predicted for 2025.
Mm-hmm.
If that works, then they will effectively refurbish already the heating systems. Mm-hmm. And then I think we will get the first high power plasmas in 2030. And then it will take years, I guess, to build the right scenario before we can produce fusion.
Mm-hmm.
So 2035. If that's mañana, that's mañana.
Yeah, just a moment. Yeah, go ahead.
When you start controlling these modes, I first understood that you were talking about just one mode, but it's multiple modes at the same time, and that's exactly why you had to move from a PLL to a Kalman filter. Is that correct?
The Kalman filter was a bandwidth problem. So the way that I discuss it here is we have a machine in the south of Germany called ASDEX, where you have a bandwidth of 5 hertz all the way up to 20 kilohertz. There the PLL didn't work anymore. Then the second part, I showed you that we also have a different observer, and this different this observer takes into account the nonlinear PDEs of the transport problem. So that's a very different problem, and indeed, that is a different beast altogether. You couldn't do that with the original one.
Yep. Okay. Please.
I'm thinking, after a lot of experimenting and working hard for years and years, trying to understand the most complicated process inside this tomahawk machine, but what do I get from that in my house in the year 2050, 60, you know?
Okay, well, that's a clear question. Thank you. Marco.
It's not a simple question at all. So what we want to produce is effectively carbon dioxide, unlimited, clean energy. That is the promise, right? Also, high temperature heat, which is very relevant for certain industries, chemical industries, let's say metal production, that sort of industries. Having said that, you also have to look at the competition. We have, of course, renewables that are now kicking in. The renewables are penetrating the market now. If the storage problem would be solved, then I think you could make the case that there is maybe no room for fusion in an energy market where you have renewables and storage. Another competitor is, of course, the generation 4 nuclear. These are effectively our direct competitors. In my mind, if we have an energy system that is based on renewables and storage, and that would work, it would mean that we are in a very good position. So I'm not trying to, that must be very clear, I'm not trying to push fusion as a solution. I'm trying to push fusion as an option. We must, in my mind, we must develop the option and be in a position that we can play the card if needed. But I would love that we don't need to play the card. I mean, I can show you with great pride the ITER site, but to be honest, if you think in terms of a reactor design, you don't want a reactor that complicated. You want a simple thing, right? So if we need to go that route, we must be able to do so. If we don't need to go down that route, it's so much better.
And could you say a bit more about the pollution of such the ITER reactor? A nuclear plant which works with fission produces a lot of nuclear waste, which will take 100,000 years to become clean again. How is it with these type of reactors?
This is a very different beast in terms of nuclear pollution. We have these high energy neutrons. They impinge on metal structures in the reactor, and they will produce secondary isotopes that are radioactive. The decay time is less than 100 years. So
Okay.
the models indicate that within 100 years, the radiation that you have left is, let's say, the comparable to the radon that you have from carbon. So
Okay.
in that sense, it's not a problem. Tritium is a big problem. If we would have a tritium incident, tritium is, of course, hydrogen, binds with water. Your body says, come on, I love water. So tritium incidents are very, very big problem. And tritium safety is a very big issue.
Okay, okay. And one question about Twente. You mentioned our engineers at Twente. They solved a problem inside the ITER reactor.
Yeah.
What exactly did they find for clever kind of solution?
Well,
I'm curious.
the solution, I must say, I'm out of my depth, but I can show you the component that they solved.
Yes, please.
In fact, I've mentioned it before.
Please.
So
What
So
part
these-
did we?
these coils, so the primary of the transformer, so to speak, and
Oh,
those.
here's a person. Sorry, I was looking for some
Yeah,
reference.
yeah.
Aha.
Yeah.
Yeah, it's big. Okay. Yeah, please continue.
So the primary and these pink coils
Yes.
are superconducting coils. The strains that they need to withstand are enormous, and the original design of the strains, the strands, I think the strands was such that they couldn't withstand those forces, those stresses.
It's just a pressure. Yeah.
And the Twente design enabled then that the coils could take those stresses, and that allowed that those big superconducting coils could be made.
Okay. Cool.
So it's a key component of the machine.
Yeah. Cool. It's good to know. I give the mic to you.
Nice picture, a very complicated machine. How many of these machines do we need if we want to provide the complete Netherlands for energy?
Well,
Only one or two, or?
No. So a fusion. This is, as I said, an experiment. A fusion reactor will be slightly bigger. That will produce 4 gigawatts. So you have then to divide the Dutch energy consumption by 4 gigawatts, and assume that we run all the time, which we won't do. So you have to add a fudge factor. But 2 is definitely not enough. And it's a very good question, because this is the second problem why I'm a bit cautious with presenting fusion as a solution. There's a second part, and the second part is once we have developed the technology, we must penetrate the market. And it's a really interesting problem. Let's say that we want to produce 10% of the world energy with fusion. Then we can come up with an industry that can create reactors that need to be renewed in the steady state. That's the maximum industrial capacity that you can build up. But that will also determine how fast you can rise to that. And that also means that once we have developed it, in normal economic conditions, we still haven't solved it. So there's a big difference between the technological solution and the timescale in which we can penetrate the market. I made this point very explicitly. Let me be very open. I'm not a big fan of the PVV. Often the PVV and people in that ballpark say that we don't need to address the climate problem because there will be technological revolutions that will allow a quick solution. That's absolutely not true. It is not true, because the market doesn't allow a fast penetration of that technology. We must solve it now.
Okay.
Okay.
Thank you, Marco.
Yeah.
Please pass the mic. Yeah. You're good.
In case it's an experiment, in case the plasma gets out, what is going to happen? Are all the rings broken?
No.
Yeah. Can the plasma escape from the?
The plasma can. I mean, if let's say the plasma gets out, as in it touches the wall, that's not a problem. That's not a problem. There is one problem, really a big problem. There is a sudden termination of the plasma altogether. There is an instability. In fact, it's the same one that I've shown you that can lead to a sudden termination of the plasma. Then you have, of course, 15 megaamps of current that suddenly stop flowing in the plasma, and you have Lenz's law, so it wants to flow somewhere else. Now, guess where it's going to flow? There. And that will create dramatic stresses, and that could lead to machine damage. So this is also the reason why we first and foremost need to have these controllers that can recognize that you are entering or try to avoid that you're entering a regime where you start to produce these modes. And then you need a real-time control system that can reduce those modes, and at the same time you will start to ramp down the current in your plasma. The timescales are such that if you can suppress the mode or avoid that the mode starts to grow and lock, then you have plenty of time to ramp down your current. But that is, of course, a big issue.
Your colleague, Tony Donnet, he was here a couple of years ago, also a fusion expert. He told that at JET, the English reactor where you also worked, that happened, sudden, and then the whole installation went, and it's pretty heavy, I think. Could you say something about it, what happened?
I can tell you a lot about it. I can tell you a lot about it.
You were there when it happened? Or
No.
Okay, no?
No, we have a really nice, we have an electronic logbook at JET, so I could search for this event. And it was done by somebody from Holland. But it wasn't me. So what happens is it's very beneficial to make the plasma column not circular, but elongated, as you see here. When you do that, you are setting up a system where you effectively have a current carrying ring, and two other conductors that are current carrying, and they are attracting. So if you move the system a bit up, the attraction becomes bigger and it starts to accelerate. The timescales of that instability are, if you don't have a metal vessel, are a million per second. So that is humongous. The vessel, luckily, is suppressing the instability, and will give you a growth rate of 1,000 per second. Now, in those days, they didn't know that this was going to happen. So the first one literally lifted up the jet vessel, rotated it by 2 centimeters, then it came down. So the jet vessel is literally tilted from its original position. Then, after that, they came up with techniques to have a very fast fast vertical stabilization, and this instability was effectively suppressed.
Okay. And what was the weight of the jet reactor approximately?
One Eiffel Tower, I guess.
Okay, just
half an Eiffel Tower.
Okay. Amazing. Are there any more questions? Marco, you also brought some very intriguing videos
If
with
people
you.
want to see,
About the construction of the reactor, it might be interesting. But first, we do some more questions. Okay, please go ahead.
Yes, I have a small question. In the fusion process, you create helium, but can you actually reuse that helium in further scientific processes?
Well, the key process that we need it for is the heating of the plasma. So the helium should collide with electrons and transfer its energy within 7, 8, 10 collisions. Then the helium is thermalized, and effectively it's an ash, and we need to get rid of it. So then there is a transport mechanism to transport the helium from the core of the plasma to the plasma periphery, and in the end it comes to this diverter structure, which I mentioned a number of times without mentioning it, and then it's pumped away. The amounts that you produce are so small that it doesn't help you.
Okay, thank you, Marco. There's some more questions over here. Please go ahead.
When we consider the resources, because this is always a problem with most energies, is how much tritium and how much helium is used within a typical reactor.
Is there enough resources for this?
So this is indeed a key question. Tritium is being produced in so-called can-do reactors. This is a Canadian reactor design, and this is, for example, a reactor design is also widely used in Romania. So those reactors produce a lot of tritium. And initially we will start ITER with tritium from can-do reactors. But that, if that is how we were going to do fusion in a real reactor, it would simply be economically unviable. What we need is a structure in this periphery which uses the neutron. The neutron will impinge on a lithium-containing salt and then will produce helium, 2.5 mega-electron volts, and a triton. And this triton must then be filtered out and put back into the reactor. This, I mentioned there are a number of Achilles tendons in fusion. This is another Achilles tendon. What we need effectively is one neutron produced in the fusion reactor, producing one triton with 100% efficiency. Now the way we do it is we use structures to increase the number of neutrons, so that is helping us. On the other hand, we have all sorts of structures where we lose neutrons. And the balance between how much neutrons we can multiply and how much neutrons we lose, and then how effectively we can build this so-called blanket structure, will determine effectively the price of fusion. So that's the magnetic field coils, the vacuum vessel, and the blanket will determine the price of fusion. And these are humongous prices.
Okay, thank you. Yep. Go ahead.
What type of material is the inside of the ring, because it needs to withstand such high temperatures of the plasma?
This here is tungsten.
Yep.
This here is beryllium. That is an ITER choice that was made early on. But there are all sorts of other concepts possible. We are very interested in working with a liquid wall. So we have done a lot of experiments in our linear device where we have liquid lithium as a metal wall. So the plasma is effectively impinging on a pool of liquid lithium which is contained in the capillary. And it has very, very strong benefits. It starts to produce a bit of vapor, which is effectively producing a cloud on which the plasma is pressing. You start to radiate a lot, you start to cool down a lot before your particles impinge on your underlying structure. So that is a very, very big benefit.
Mm-hmm.
So that is another solution.
Yeah.
Then there are people that simply say this should be stainless steel. Another possibility. There are people that say this should be diamond. I'm not kidding you.
Mm-hmm. And Marco, what do you think it will be? Because that's still the question. The invention.
I think that we will end up with a tungsten, completely tungsten reactor.
Mm-hmm.
That is the reference solution for demo. Completely tungsten.
And will the liquid solution from Eindhoven also be used somewhere, or?
If tungsten, so the way it works, if tungsten is going to be proven to withstand, then tungsten is the right reference material.
Okay. Yeah.
Our solution is a backup, but it's a very interesting backup.
Mm-hmm. Okay.
Yeah. So you mentioned that tritium was dangerous. In what way is it dangerous? Is it poisonous? What would happen if you swallow it?
Marco,
well,
please tell us.
It is dangerous in the sense that it is an intense radiating material with a very short lifetime, I think 12.5 years. The real problem is that, as I said, it connects with oxygen and forms water. And your body just loves water. So it's very easy for your body to take in tritium, and it will be transported throughout your body, throughout very delicate regions. So you have an intense radiating material which can be everywhere. Mm-hmm. So it's really serious, and I think we know very well how to confine the tritium. We can confine them in metal lattices. Nevertheless, the tritium safety is a big concern in ITER.
Mm-hmm. Okay. Marco, to round off a little bit, could you say something about the design of the stellarator reactor? Because that's some kind of worm-like thing. This is a very symmetrical design of a reactor.
I have to search.
But there is in Greifswald, you told me during dinner. Maybe you have seen it when you Google for stellarator.
Let me show you.
What does this solve? Please explain. Why
well, I explained to you that we needed a poloidal magnetic field in order to deal with those particle drifts. Mm-hmm. And in order to do so, we are driving a current in the plasma. What the Wendelstein team has done is said, well, we can produce this toroidal magnetic field using coils without driving a current. But in order to do so, you must produce these very special coils. And these are all superconducting, for your information. And then, when you have this system set up, and you can do really first principle physics optimization, how this structure should be in order to get the optimum compensation for the drifts, and then you can calculate what the coils should be, you get this very complicated structure, which has been constructed. It is in the north of Germany. This is a €1 billion project. Everything big, everything superconducting, and it works like a dream. So this is yeah.
Okay.
I'm a big fan of this project. We don't do a lot of work with them. We do some work with them, but it's really, really good stuff.
Amazing that they actually built this. Okay, and then we have in Canada, we have the Global Fusion Project. To explain it very briefly, it's a globe with inside a plasma, and then you have all kind of injectors, explosion things, which compress the plasma to such pressures that there can exist fusion inside this globe. Could you say something about that technique? Is it likely to produce real fusion? Well, how do you see that project?
Well, as a scientist, I don't want to make statements that I haven't calculated. Let me just explain what the principle is.
Yes, please.
The idea is that they have a liquid metal in which they confine the plasma. Then they have a set of, and this is on a sort of spherical device. Then they have a number of humongous pistons, and these pistons can be fired to compress the liquid metal ball with very high degree of synchronous timing. And that means that the ball is going to compress. The plasma that you have in the ball is also going to be compressed, and they claim that with that technology they should be able to reach transiently conditions in which they produce fusion. The philosophy of the team is fantastic. They say they will not use anything on the machine that they can't buy in the Gamma, Home Depot. To be honest, this is not completely true because I have never seen pistons of that size. But the philosophy is that they try, and I admire them for that, they try a method which is almost orthogonal to the main line, and they could be successful. It's a private company, you can buy shares, and if I'm allowed a non-scientific statement, I don't have shares.
Okay. But it's nice to follow it, of course.
And if they succeed, good for them.
Yeah. Okay. Maybe it's nice, Marco, to round off with one of your videos. Is that a good idea? Just to show a bit about the construction of the
ITER will be the world's largest experimental facility to demonstrate the scientific and technical feasibility of fusion power. 30 meters in diameter and nearly as many in height, the ITER tokamak will house a large number of subsystems and components. The size and weight of the major components, the tiny tolerances for the assembly of major systems, the diversity of manufacturers, the tight schedule, all of these elements combine to make ITER an engineering and logistics challenge of enormous proportions. The principal assembly activities will be performed in the tokamak building, where the ITER device will be installed inside of a partially embedded concrete bioshield. For the duration of assembly activities, the tokamak building will be operated as a clean area and maintained at a constant temperature to avoid dimensional changes in the largest components. Pre-assembly activities will take place in the adjacent assembly hall. Assembly of the ITER tokamak will proceed in a bottom-up fashion. First, the lower feeders for the ITER magnets will be put in place. Then, the base of the cryostat, the largest single component of the ITER machine, is lifted into position. The next components assembled are the lower cylinder of the cryostat, thermal shields, and the temporary support structures for colloidal field coil number 6, the smallest of the set of 6. A set of spare pre-compression rings are the next in line, together with the central support structure and the 18 gravity supports for ITER's huge toroidal field coils. Thermal shields that will protect the steel support structure are then attached. And finally, poloidal field coil number 6 is lowered into the pit, followed by PF coil number 5. In order to prepare for the arrival of the pre-assembled vessel sectors, the inner support column, the work floor, and the 7 beams are put in place to stabilize the structure during the assembly phase. While the cryostat is being assembled in the tokamak hall, parallel activity is in full swing in the assembly hall. It's here where the sub-assembly of the 9 40-degree sectors is being prepared, each set made up of a vacuum vessel sector, the surrounding thermal shields, and 2 toroidal field coils. In order to successfully maneuver hundreds of very large tokamak components into position, a very precise made-to-order set of tools is currently under construction. A special sub-assembly tool will suspend each of the 9 sectors of the vacuum vessel from its top, install associated thermal shielding, and rotate 2 toroidal field coils into position. This procedure will be repeated consecutively to achieve 9 sub-assemblies, which will be transferred into the tokamak pit for the final sector assembly. The lifting system will be comprised of a pair of independent bridge cranes, mounted on rails that run the entire length of the tokamak and assembly halls to form a continuous 175-meter-long crane bay. Working together, the 4 375-ton main hoists will handle loads of up to 1,500 tons. With more than 18 meters height, the central solenoid, the magnet in the center of the machine, will be the tallest lift of assembly operations. The heaviest single load will be the base of the cryostat, which weighs in at 1,200 tons. In some cases, components standing 20 meters high and weighing hundreds of tons will have to be maneuvered into position within tolerances of 2 to 3 millimeters. The accurate alignment of the tokamak components, particularly of the magnet system and in-vessel components, is essential to the successful operation of the machine. Assembly sequences have been planned with this in mind and will utilize sophisticated optical metrology techniques at each step of the assembly process. In all, 161 different types of custom tools will be required to assemble, lift, and finally maneuver ITER's supersized components. The tools will have loading capacities that vary from 500 tons for the upending tool that will turn vacuum vessel components from horizontal to vertical, to 1,500 tons for the heavy lifting tools, used to lift the sub-assembled sectors into the tokamak pit for final assembly and welding. There, the largest purpose-built tool, the in-pit assembly tool, will grasp all 9 sectors together, 3,800 tons, in order to align the vessel structure. The complete assembly of the ITER machine will take about 4 years. Following main assembly and alignment of the vacuum vessel, the second assembly phase, the installation of in-vessel components, will proceed with specialized remote handling devices.
Wow. Marco, we have to round off, unfortunately. Marco, may I thank you very much for coming to Enschede and showing us around in the world of the fascinating world of fusion
really
physics.
My pleasure.
Okay, ladies and gentlemen, a big hand for Marco. Thank you very much. And thank you very much. Yeah.